So, I will talk on errors in measurements. The material and heat balance calculations, they are based on several assumptions like stoichiometric requirement of the reactant and accordingly the production of the product. Also, we take several values on heat of formation, specific heat capacity, heat of reaction at 298 Kelvin. So, based on all these assumptions, after doing material and heat balance, we make certain predictions. So, we make predictions, for example, mass flow rate that is entering into the system and mass flow rate that is exiting the system. Another prediction that we make by doing heat balance calculation is that of the temperature. Still another predictions we would like to make about the gas flow rates. Now, suppose in a process air is required as an oxidizing medium. You predict the amount of air that will be required, and that prediction is based on a stoichiometric amount or a stoichiometric requirement of the reaction. So, you would like to see that whether these predictions are correct or not. So, you would like, so gas flow rates are also one of the important output. Then certain amount of weights are being put, 100 kg, 200 kg, you are measuring certain amount and you are putting into the system for the reaction. So, what I mean to say is that the objective of material and heat balance calculation is to predict these outputs so that one can control the process. Now, the predictions are also required to check through measurements. That means, if we can measure these values, then online we can measure the predictions and we can accordingly correct our material and heat balance energy formulation, because we are making certain assumptions while calculating the outputs which I have mentioned earlier. So, therefore, the errors in the measurement, they are very important issue. You know how you are going to measure? Suppose you want to measure the mass flow rate of the gases, then you will use the sort of rotameter, or you will use mass flow meter, or if you want to measure the volume flow rate, you will be using say rotameter. You want to measure pressure, you will be using some type of sensors. Similarly, you will be measuring temperature, you will be measuring through thermocouple or through pyrometer. So, all these measuring devices, they have certain errors in measurement. So, accordingly, let us discuss what are the errors in measurement and how they interact with each other. Now, in fact, the errors in measurement, they interact with each other. Now, again here one should be also clear that something like error tolerance. Now, this error tolerance means how much amount of error you can tolerate in the measurement of a physical quantity. Now, this error tolerance, it depends upon the magnitude of physical quantity, depends upon magnitude of the physical quantity. Now, with that I mean, for example, stainless steel contains say 9% nickel. Stainless steel contains 9% nickel and you are making an error in chemical analysis, say error in chemical analysis, of nickel, say consists of plus minus 0.0 0.05%. Then probably in that magnitude of 9% nickel, this 0.05% error in chemical analysis, that may not be that significant, it may be total insignificant. But suppose if you are measuring say hydrogen in steel, if you are measuring hydrogen in steel and you are making an error of plus minus let us say 0.2 ppm, where the magnitude involved is of the order of say 2 ppm, then this 0.2 ppm though looks to be very small in number, but it has lot of significance. That means, this measurement is considered to be highly inaccurate. So, what I mean that accuracy or inaccurate measurement, it can be judged in relation to the magnitude of the physical quantity. It depends upon what is the magnitude of the physical quantity. Now, actually the true value of any measured physical quantity is not known. What is the true value? We do not know. So, what we do is that we make several measurements and we take a mean of several measurements and say, well, this is approaching to the true value, or we call this is the true value. So, we say mean, rather arithmetic mean, say x bar, that is equal to sigma x I upon n, that we can is used to describe true value, to describe true value. That means, the residual say d I, that is equal to x minus x bar, that determines the what is the say accuracy of the measurement. See, for example, if we say d I is small, then we say measurement is precise, but a precise measurement not necessarily be accurate. An accurate measurement can be precise and can also not be precise. That will depend upon what is the say residual content between x and x bar. So, in general, the normal distribution of any measurement, it describes say accuracy and precision of a measurement, That means, this any random variable y, say normal distribution, say any random variable y, that is equal to 1 upon sigma square 2 pi e to the power minus x minus mu whole square upon 2 sigma square. Now, here x is a normal random variable, mu is the mean and sigma is the standard deviation. So, the graph of the probability function as described by this normal distribution function, it will depends upon the value of mu and sigma. The mu determines the center of the graph and sigma determines the height and width of the graph. So, if I want to plot, for example, let us take some different situation. Say I plot here probability density, I put this is the center of the graph, then this is how normal distribution appears. Say this value is called mean and this one is the sigma. If I say sigma 1, because I want to compare the other one. So, let us take it another type of distribution. Same probability density on the y axis, this is the center of the graph. This one let me take sigma 2 and this is again the mean value. Now, as I said that the sigma, it determines the height and width of the graph. So, here you are seeing here that sigma 1 is greater than sigma 2. So, now in terms of say precision and accuracy, let us consider again this type of function. This is again say center of the graph and let us take this is somewhere here is our reference value. This we call as a reference value. This is the reference value and our distribution is say something like this. So, this particular difference that is called accuracy and this is called precision. That means, you can also understand that sigma is the standard deviation is also called spread of the distribution function. You can also consider it decides the precision of a measurement. Number 2, the normal distribution is symmetric in nature, it is a bell shaped curve. So, that is what the typical of the normal distribution. Now, the error, there are different type of error that one can do it. One of the error, let us say, is the random error. Now, random error normally depends on the mood of the person. That means, when he is measuring what is his mood and how he is reacting to a particular measurement. So, in fact, the random error, its effect can be shown on normal distribution like this. Say this is again the center of the curve and then so this plot, if I take the distribution without random error, and the same person is making it. Now, this distribution is with random error, because sometimes his mood is good, he may read more value, his mood is bad, he may read less value. So, that is why you are seeing the error or the random error in measurement, it does not affect the average value. So, we can say the random error no change in the mean. So, we are seeing the mean is same in both the measurements. So, no change in mean, but there is a change in sigma. That means, now the dispersion it increases. So, if you want to determine the true value, then measured dispersion square, that is equal to true dispersion square and plus ER square, where ER is the magnitude of the error due to random error. So, now suppose if let us say measured dispersion, let us say measured dispersion corresponding to 8 units and ER it corresponding to let us say 6 units, then true dispersion that will be coming out to be equal to 5.3. So, that is how one can determine what is the true dispersion. Now, another type of error is the systematic error. Now, similarly systematic error can also be shown on normal distribution plot. So, this is the now by term systematic error, that means you are making error systematically. So, you can very well visualize it may not affect the standard deviation, but it may affect the mean of the measurement, because they are the systematically error. So, accordingly if I want to represent, say this is one situation, this is another situation. So, one and here. So, what you see now from here, this particular curve is the distribution of x with no systematic error, and this is with systematic error. Now, here of course, the probability density, here also probability density. So, here what you note from here, that there is change in the mean has occurred. So, systematic error affects mean value. You see the mean has shifted towards the left when your measurement has systematic error, but it did not change the standard deviation. So, we are seeing this value is more or less same as to this value, whereas here you see this was the standard deviation in one case. Now, in the another case this is 1 and this is 2. So, the systematic error it does not affect the so called standard deviation of the distribution. That means, the dispersion may remain same, but it will affect the mean value. So, one has to see that what you are measuring and what type of error you are doing. Now, say distribution with mu is equal to 0, a distribution with mu is equal to 0 and sigma square is equal to 1 is called a standard normal distribution. Is called a standard normal distribution, and it can be represented by say f x, that is equal to exponential minus x minus mu upon whole square upon 2 sigma square root of 2 pi, and this is valid for minus infinity less than x less than plus infinity. Now, in most of the situation, the mu, which is the mean of the normal distribution, with the true mean is not known. So, what is being done? We determine the standard deviation by making a large number of measurement, and by using the formula S. I think all of you know the standard deviation of any measurement, it can be determined through this formula. I is equal to 1 to n x I minus x bar whole square upon n minus 1, and we say S, it approaches to sigma in the limit of large number of measurements. So, what we can say is that x bar and S, they can be used as an estimate for mu and sigma of the normal distribution. Now, say we define Z, we define say Z that is equal to x minus mu upon sigma, that is approximately equal to x minus x bar upon S, because you know mu and sigma of the normal distribution, they are not known. So, we estimate, we make large number of measurement and we find out x bar and we find out S, and then we define again a function f z that will be equal to say exponential minus z square upon 2 sigma root 2 pi. So, now in this what we can say now, if x is a random variable, if x is a random variable distributed normally with mu and sigma, because once we specify mu and sigma, we can trace out the graph. Then Z is distributed normally, Z is distributed normally. I mean, I am using the word normally is not in the literary sense, normally means normal distribution, do not think normally means normally. Z is distributed normally with mean equal to 0 and sigma square is equal to 1. So, in this particular form, the total area under the curve, say f z dz minus infinity to plus infinity, that is equal to 1. That is what under the condition when mean is equal to 0 and sigma square to 1, the total area under the curve becomes equal to 1, and the normal distribution, it looks something like this. This is the one. So, 1 and now this is a symmetrical So, now this one, that this value is 0, this is sigma, this is also sigma, this is 2 sigma, this is 2 sigma, this is 3 sigma and this is 3 sigma. So, that is this is a transformed normal distribution by putting value of z and what I have said earlier. So, in this form what does it mean? It means say 68% of the data they fall within one standard deviation. 95% of the data, that is in this area 68% of the data will fall with one standard deviation, then 95% of the data fall within 2 standard deviation about mean, and 99.7, in fact all data 99.7% of the data fall within 3 standard deviation, 3 standard deviation. So, that is what the accuracy and precision means. That means, if you want precise value, then the standard deviation should be small. So, all these things are I have explained here. Now, let us see the propagation of maximum error. propagation of maximum error. Propagation of maximum error. Now, this one is the addition and subtraction method. Addition and subtraction method. And subtraction method. Now, say when errors are small, then this method can be used. Now, suppose you have a final result which is u, and it comprises of measurement on x and measurement of y. So, that your final result that you are going to report, that is the value of u, it consists of the independent measurement of x and y. So, that u that is equal to x plus y, that is u I call as a final result. This is the final result which is based on, say, x and y are independent measurement. They are the measurement and you sum total and you report the value of u. So, now say I can just put it du that is equal to dx plus dy, or in terms of finite increment I can say delta u delta x plus delta y. So, if error in measurement, if error in measurement of x, in measurement of x is delta x and error in measurement of y, error in measurement of y is delta y, then maximum error that will be equal to delta x plus delta y. Now, let me illustrate by taking a particular problem. Suppose in various, say for example, in metal extraction, in copper extraction, you roast the chalcopyrite concentrate and you prepare a blend of chalcopyrite and lime. So, a blend of chalcopyrite and lime is made by weighing chalcopyrite and lime independently, and then they are mixed into a container and then they are fed into the plant. Now, chalcopyrite has an independent measurement of the weight, as well as lime has an independent measure of weight, like x and y is the two quantities. Now, say let us say chalcopyrite feeder, it weighs the feed rate, say 100 kg per minute. Now, there are mass flow rate sensors which can measure the feed rate. All that these sensors are to be put in the feeder and you can accurately get the weight, but it has certain error. So, let us say chalcopyrite feeder weighs the feed rate 100 kg per minute with, it will have some accuracy with, let us say, plus minus 2.5% accuracy. Plus minus 2.5% accuracy. Now, let us take lime, because we have to make a mix of both. So, let us take lime, and lime is fed at the rate of 10 kg per minute. That means, you are having a big container and from the container certain mass flow rate of the lime is being out, and at the outlet you have put a sensor and it is measuring what is the rate of output of the lime, and that rate is 10 kg per minute, and it is measuring with an accuracy of let us say plus minus 3%. Then what is the mass flow rate of the resultant feed? What is the mass flow rate of the resulting blend? That is what we have to see. And now, as what we have done earlier, so error in chalcopyrite, and you have error in lime. These are the two error. So, error in chalcopyrite, that will be 100 into 2.5 upon 100, that will be equal to 2.5 kg per minute. Of course, that will be plus and minus. Error in lime, that will be equal to 0.03 into 10, you have plus minus 0.3 kg per minute. So, the mass flow rate of blend, that will be equal to 110 kg per minute plus minus 2.8 kg per minute. Now, this is an illustration that all the measuring instrument, they have certain error in that. So, these errors are to be accounted while correcting the predictions made by material and energy balance. That is why this is the importance of, that is what the importance of these measurement. So, here the mass flow rate of blend will be 110 kg per minute plus minus 2.8 kg per minute. So, the another way, let us find out one of the another thing is that of multiplication and division method. Multiplication and division method. So, for example, if the final result, now in an earlier case, in the final result we are adding the two values, two independent measurements were added and we get the blend. That is why we use addition method. And the error in each measurement we have added up and we have said, well, the final blend consists of this plus minus that error. Now, here say if the final result, is the product of two measured quantities, the final result is the product of two measured quantities say x and y, product means multiplication, I mean say u is the final result that you want to get of the measurement, say, and it is in the form of a product, say u is equal to x into y, then we can say du that will be equal to x into dy plus y into dx, or we can also say du upon u that will be equal to dy upon y plus dx upon dx. Now, say if error in x and y is small, then the error delta u in u, it can be calculated from delta u upon u, that will be equal to delta y upon y plus delta x upon delta x. Now, say we can also report these errors in terms of percentage error. So, reporting errors in terms of percentage, reporting error in percent, that will be equal to delta u upon u into 100, that will be equal to delta y upon y into 100 plus delta x upon x into 100. So, let me illustrate this thing by an example. So, let us take the volume flow rate of oxygen, the volume flow rate of oxygen in a flue gas stream, say is equal to, for example, VO2, that is equal to V flue gas into percent O2 upon 100. That is the volume flow rate of oxygen in a flue gas is given by this one. Now, if V flue gas is 1200 plus minus 60 meter cube per minute, it is measured as 1 atm and 0 degree Celsius, and oxygen analysis is 5% plus minus 1.5%, then what is the estimate of, VO2 in flue gas? So, we can say VO2, that will be equal to 1200 into 5 upon 100, that will be 60 meter cube per minute, but delta VO2 upon 60, that is equal to 60 upon 1200 plus 1.5 upon 5. Therefore, we get from here, we get delta VO2, that will be equal to 21 meter cube per minute. So, therefore, value of VO2, that will be 60 plus minus 21 meter cube per minute, or you can say the error would be 35%. So, you can see now how this error in measurement helps for the estimation purposes. Now, this result can also be obtained by adding percent error in each measurement. For example, percent error in total flow, that is equal to 60 upon 1200 into 100, that is equal to 5%, and percent error in analysis, that is also there, say 1.5 upon 5 into 100, that is 30%. So, total error has become 30 plus 5. So, percent error in oxygen flow, that is again 35%. So, this way also you can do it. Now, another that I have to illustrate the propagation of probable errors. The propagation of probable errors. Now, the probable error P in, for example, measured quantity u, it can be given by P, that is equal to plus minus, if the independent variables are x, y and z, then the probable error P plus minus the u upon delta x whole square P x square plus delta u upon delta y square P y square plus delta u upon delta z square into P z square. Here we took 3 independent variable x, y and z, where P x is the probable error in x, P y is the probable error in y and P z is the probable error in z. Now, let us take an example, say volume of a hemispherical reactor. Let's take volume of a hemispherical reactor say is given by V, that is equal to pi d cube upon 12, where d is the diameter of the hemisphere. Now, diameter is measured several times, several locations, and you determine an average of several measurement. That means, diameter is measured, or several times, you made several measurement, and the average of several measurement in diameter, in diameter of the hemisphere in dia is 2.42 meter. Probable error in determination of diameter. So, let me write probable error in determination of diameter, let us say is plus minus 0.015 meter. Then calculate the probable error in volume. Calculate the probable error in volume. Now, you see this is a typical example of how the error propagates. You have done some error in measurement of diameter, so it is propagating through, and ultimately that error will be reflected in volume measurement. Similarly, when you do the heat balance, if you do some mistake in material balance, that error will be propagated throughout the heat balance calculation. So, that is a very serious error about the propagation, that is an important thing. So, we can find out say P that is equal to plus minus, we have only one variable. So, that will be delta pi d cube upon 12 delta d, that is what our formula, into P r squares, or we can write P d square. We are measuring the diameter, only one variable. So, the equation reduces to that. So, we rather differentiate and take the root, then we get say plus minus pi d square upon 4 into P r. I substitute the value plus minus pi into 2.42 square upon 4 into 0.015. So, ultimately I will be getting plus minus 0.0284 meter cube. So, the calculated volume would be you can calculate volume by substituting d is equal to 2.42 meter, that will be equal to 3.71 plus minus 0.0284 meter cube. So, that is what the propagation of error means.
Sir, I have a doubt. Sir, can you give me an example of maximum error using subtraction method?
Though in the lecture I mentioned addition and subtraction method, I can give you an example of the use of subtraction method to find out the error. Now, let us take the same example of blende and limestone and chalcopyrite. So, let us take now the blende, take it consists of 100 kg per minute, it is an error plus minus 4 kg per minute. In our equation, let is called u. Now, say chalcopyrite, let us say chalcopyrite, and this chalcopyrite, let us say we have 80 kg per minute, and with an plus minus error of 1.6 kg per minute, and let us take this is an x. Now, so let us take find error in lime, find error in lime, and let us call this is say y. Then as for equation we have u, that is equal to x plus y, then we get y, that is equal to 20 kg per minute, of course 100 minus 80, 100 kg per minute. Now, you know that error was delta u, that is equal to delta x plus delta y. We have to find out delta y, that will be equal to delta u minus delta x. Now, here delta u we have 4 kg per minute. Now, here one has to be little think over, because if you want the maximum error, then we have to use the minus sign of chalcopyrite, then it is minus say minus 1.6. So, that becomes equal to 5.6 kg per minute. So, error in lime that will be 20 plus minus 5.6. Now, in fact, error in lime is 5.6 kg per minute. So, the weight which you are reporting, that the total with error, that will be 20 plus minus 5.6 kg per minute. Is that your question?
Yes, sir. Thank you, sir.